So I would like to talk today about the ways in which programs and proofs can interact. And I'm going to start this with a small and very crude taxonomy of how you could build a system that somehow brings programs and proofs together. So I have three categories here. The first one is where I write code in a normal mainstream programming language, and then I have some kind of system that then lets me prove things about this code. And I think there are many examples of this. We have a system in the Lean world called Aeneas, where you write regular Rust code, and then you have a system that gives you ways to prove statements about this Rust code in Lean. There's a similar tool called or not similar, but there is a tool called autochorus that does something vaguely similar for the C programming language and the Isabelle theorem prover. And then we also have systems which where you don't land in these interactive systems like Lean or Isabelle, but ones where you generate some kind of verification condition that is then dispatched by an SMT solver. So we have this for something like C. In Frommer C, we also have liquid Haskell, which does something similar for Haskell. It lets you attach invariants to Haskell types, and then an SMT solver proves that these invariants are upheld. And the characteristic here is that you start with a programming language that you would have started with anyway, and then you find a way to reason about them. You can also go the other way around, where you start with a system that somehow knows about verification, and then once you have done your verification, you extract or compile this to to programming language that you already know. So in this category, you could locate something like Daphne, where you have a verification-aware programming language that then is extracted to C# and many other languages. And you could also argue that a system like Rock could fall in this category where you write your code in Rock, verify it, and then you have program extraction to OCaml, another mainstream programming language. And then there's a third category, and this is what I'm going to focus on today, where you have the whole package in one. So you have a programming language that is itself the programming language, but it supports verification in some way. And two technologies you could locate in this category are Idris and Lean 4. And the fundamental difference between this category and the two before is that there is a priori no strict separation between a world where there are proofs and a world where there are no proofs anymore, or there aren't any proofs yet. And the opportunities that are afforded by this fact is what I want to explore today, and I'm going to do it using Lean. So the rest of the code you're going to see today is in Lean. I'll try to make it as understandable as possible. Let's start with a very simple example, just to get you acquainted with Lean a tiny bit, if you haven't been to Joachim's tutorial this morning. So here we are going to have the usual paradigm that we first write a function and then reason about it. So here we have a function that takes a natural number and increments it. And then, so this is really code, the first two lines, and then the second two lines, we are reasoning about code. So here we're claiming that whatever we put into this function, it's going to be, the result is going to be greater than 0. And then the syntax for a definition and the theorem is actually very, very, very similar. And then the body of such a theorem declaration is going to be the proof. So everything starting from this by is the proof. It's not necessary to understand what this proof does, but Lean verifies it. And now we have proved that the result of this add1 function is always positive. Of course, the reason this works is because this nat type is really arbitrary precision integers. There's no wraparound here. Otherwise, we wouldn't be able to prove this. So Lean would reject a kind of proof. So this is the baseline. We write the code and then we reason about it. So and what we can think about is how can we switch this up, right? And I'm going to show you an example right away for this, where we have actually a proof inside code, and this is this segment here, a bit longer. The idea is very simple. We have two two arrays of natural numbers, and we want to sum up the products of corresponding elements until, as far as this was possible, so until the lengths allow for this. And we're doing this in the small imperative style program, so we have just an accumulator, and then we have a for loop which runs until the minimum of the sizes, and then we just sum up the values. Very simple. I claim that this is an example of proofs inside code, and you might wonder, okay, where is the proof here? And the way to see where the proof is to, for example, go ahead and change the min in the bounds of the for loop to a max. We can do this. And then, as you can see, we get the red squigglies for the array accesses inside the for loop. And we can actually see what the error message is. And it says here, failed to prove the index is valid. So what Lean actually did behind the scenes here is reason for us that the array accesses here are in bounds for the array, because the index never goes beyond the minimum of the two sizes. So Lean actually checked safety for us here, and if we put in a bug, we immediately get an error message. And what this hints at is that in Lean, for many operations, we actually have multiple ways to do these operations. There's the safe version, which you need to provide with a proof that what you're doing is actually safe. So we have, so for the array index notation, either you omit the proof completely, then Lean tries to do it by itself. And as you saw, if it can't do it, either because it's just not true or because it can't find the proof by itself, then it will give you an error message. And we have this explicit notation, which you can see on the right, where I can inline provide a proof that the array access is in bounds. And when we do this, the interesting thing is when we do this, the code that's actually emitted by the compiler does not contain another bounds check at runtime. So we've statically done the bounds check. There's no reason to check this again at runtime. And then if having the safe version is either is impractical for some reason, then you have escape hatches. So you can either do a checked access, which performs a runtime check and then returns an optional value, which you have to explicitly match on to see whether you were in bounds or not. Or finally, in situations where this is fine, you can also panic, as you would maybe in other languages. There you are going to get a runtime check, so you aren't going to see memory corruption, but your program might panic and, depending on how you set things up, terminate. So then it's over. And my point is that having the safe version really allows us to do this, to get many benefits at once. It is safe. It is efficient. We don't pay any kind of runtime tax. And given provided that our automation is good enough, which fortunately in many cases it is, users don't even need to worry about anything because Lean does all the heavy lifting in the background for you. So when this works well, I think it's really great. So two questions that we might wonder about is, one, how does this work under the hood? And what can we do with this? And this is what I want to spend the rest of the session on, and we're going to start with how does this work. There are actually quite a few mechanisms that we have in Lean that make these kinds of things possible. I can't talk about all of them. I am going to quickly show you two of them. And this is runtime functions and doing pattern matching on empty types. So let's jump right in. So when you run when you compile a Lean program, it links against it links statically against a small runtime that's written in C++. You can't really get around this. If you're going to build a programming language, you do need to do things like I/O, and the Lean runtime also provides some very simple primitives like numbers, but also like arrays which allow for efficient updates, which is a key thing to make Lean programs perform well. So when you do something like this array access, then you actually just call, first of all, a regular Lean function, which looks like this in our standard library. in a very, very early part of the standard library. And you can see this does have a lean implementation, which is used for reasoning, but for when this program gets compiled, what's actually generated is not the code that's written here, but a call to a function in our runtime. And of course, it's very important that this code and this code match. So we use this very sparingly, and we only provide the most basic things in our runtime. And then what you can see is, if you look at what the code in our runtime actually looks like, you see this, which is just a C function signature. And the thing that jumps out is here we actually had 4 parameters. We had the type of the elements of the array, we had the array, we had the index, and we had the proof that the index is in bounds. But if you look at the C function, there are only 2 arguments, namely the array and the index, because types are computationally irrelevant. So there's no reason to have them at this runtime level, and proofs are also computationally irrelevant. So there's no need to have them on the runtime level. But the point is, this function does have this precondition. It will only be memory safe to call if the proof is if this fact that I is smaller than the size of A is actually true. So even though it doesn't appear on the C level, it would not be sound to add, for example, this extern annotation to a function that does not check this precondition on the lean side. But because we don't do this, this is for a lean user perfectly safe. So this is one way. So this is useful. There is a big problem with this. It's not user extensible at all. It requires you to interact with C code. It's something we do when we write the runtime, but it's not something that you as a lean user can really access beyond what we give you. Luckily, there are other ways. And one of them is pattern matching on empty types. So let's have a look at this function. So the idea is here I'm given a list of natural numbers, and I'm going to do in a very inefficient way the following operation. I want the first element of the list, or if there is no such element, then I want 0. And in a very crude way to do this is first append 0 to the list and then do a pattern match and extract the head element. Because after I've appended 0, the list is no longer going to be empty. So I have this pattern matching branch for the empty list that I know is unreachable. So what do I actually put in that space? So one thing that I could do is I could call the unreachable macro, which lean has. And this just compiles to a panic, basically. So when we write the code like this, what will actually happen? We will append 0 to the list, and then we will actually, in the compiled code, perform a pattern match on the list. And if we get a cons, then we are going to return the head element. And if we get a nil, then we're going to panic. So this branch is going to be in the code, even though we know it's never going to be called. So it would be good to do better, and we can do better. For example, like this. When I'm in this situation down here, in the nil case, somehow I know I am in a situation that cannot happen. And the good thing is that in lean it is possible to express this fact. So for example, I can in my program start proving something, and in this case I'm going to prove false, which of course I can only do because I am in a contradictory context. So we can have a look at what we get here. So this is what lean wants us to prove. It gives us a list of natural numbers, and it gives us the hypothesis that this append is equal to the empty list, and it wants us to prove false. And because this is a contradiction, we can prove false here. So we do this using this very short proof. And now false is a type. It is like by the Curry-Howard correspondence, it corresponds to the set of proofs of false, which is empty. There is no proof of false because that doesn't make sense. So what we can do now is we can do a case distinction on all of the proofs of false that there are, of which there are none. So we have a special syntax for matches over things which don't have any cases, which is no match. So no match is like match, only that it only works for things that have no cases, which is true for this proof of false because there is no proof of false. So this is a way to give something here. And the compiler basically has special support for this case distinction over things which have no cases. We'll see how this looks in a moment. Let me first add one more thing, which is that sometimes you even get this for free. So here we have another similar piece of code. Now we have actually a proof as a precondition for the function that the list is not empty. And now we again want to extract the head element. And now what we actually do is we match over both the function and the proof. And this match, we match over both the list and the proof. And normally, when you match over a list, you need to give both cases. Either it's a cons or it's a nil. But because we're matching over the proof at the same time, Lean is actually smart enough to notice, okay, in the nil case, surely then this proof would be of the form the empty list is not equal to the empty list, which is clearly contradictory. So in this case, we actually don't have to write this match arm at all. Lean deduces for us automatically that it can't happen, and we only have to list this one match arm which actually can occur. So that's very nice. And behind the scenes, it basically does the same thing we had earlier. It just derives the contradiction for us. And now let's have a look at how this looks to the compiler. So here we see the internal representation that Lean uses in the compiler. So this is a completely new syntax that you most likely haven't ever seen before. And here we are now doing a case distinction over this L. Luckily, it still has the same name, so we know what it is. And then in this nil case, which we have just argued can't happen, and we have this bottom symbol, which is basically short for this is unreachable. And then in the cons case, we project out this first field, which is the head element of the list, and then we return it. And this and looking at it like this is somehow manifestly safe because in this case down here we're doing the projection if we know that we're in this cons case. So we have in this version of the code we still have the pattern match, and so we know that projecting is valid. If we in this nil case, projecting would not be valid. But now in the next step, the compiler notices, okay, unreachable code is unreachable, so I can remove the entire case distinction. This is probably impossible to see for most of you. Sorry about that. Maybe I can move away the chair. Or I can just read it out to you. So here we basically only have these two lines left. The compiler just in one of its simplification passes deleted the first 4 lines and de-indented those 2. So now we're just unconditionally projecting out this head element of the list, which considered on its own would be unsafe. But we know because of the proof that we heard earlier that this is actually safe code, and it will be fast at runtime because you're saving a branch. Okay, so these are some mechanism of how proofs can influence the Lean compiler. I want to do a quick comparison to another programming language, namely Rust. So Rust has an unreachable macro, which is basically the same as the one we have in Lean. It compiles to a panic. It does not allow for most optimizations. Rust also has a function or an intrinsic called unreachable unchecked. And this is designed to do the kind of signaling to the compiler that we are also trying to do. so here I'm in the. So here I have a. I have in this case a slice of data, and I have a slice of indices which supposedly point into that data. And now I really promise that that all of these indices are in fact valid for this slice. And now I want to sum up all the data at the given indices. So I'm going to fold over the indices, and now I want to accumulate the data. But I really promised that the indices are in bounds for the data, so I would like to omit the bounds check. And I can do this in Rust, and I do it in this way. I'm going to perform the bounds check for the compiler, but then in the case that we are out of bounds, I'm going to call this unreachable unchecked function. And you can put this into like you can look at what this compiles to, and you see, yeah, the runtime check, the bounds check is not there. So the compiler does understand this. We can do the same in Lean. It's basically the same code. Most of the functions even have the same name. Of course, the syntax is a bit different. The main thing that changes that now, instead of having this human language safety block and the unsafe keyword, we just have a proof in the function where we are saying for all of the i's in this indices array, the I is less than the size of data. And then I'm going to perform, just like here, I'm going to iterate and I'm going to fold. Again, here I'm going to iterate, I'm going to fold. It's basically the exact same thing. And now I'm providing the proof that the array access is in bounds. And again, if you look at the code that this generates, you'll see there is no bounds check. So these are both cool. We can do these both. There are reasons why I think this is preferable over that. One is, of course, the compiler is helping us much more here to make sure that we don't do anything problematic. In Rust, we do have to mark this function as unsafe because it does have a precondition that is not enforced by the compiler. So the compiler is not going to help us ensure in any way that the indices are indeed inside the slice. We need to check it ourselves. We need to properly document things, and we can make errors during that. In the Lean example, you need to do the proof in a way that the Lean compiler accepts, which is, of course, a much higher hurdle than just putting a comment somewhere. And if the Lean compiler accepts it, you can be quite confident that it is really true. The next thing that I want to point at is that the way the conditions flow through the program are more explicit in the Lean version. So here, I'm basically I'm doing the check, then I'm just going to do the access. I have nothing in the code that specifically tells me that the compiler is going to understand that I did this check here and did this assertion correctly. Maybe the compiler only understands this if I do if not data.len smaller than I or something. Maybe it doesn't understand that this is supposed to be an assertion about this operation here. We don't have anything in the Rust code that ensures that this works. The only way we can really see that the compiler did the right thing here is, one, look at the disassembly, and two, maybe even more importantly, do benchmarks, which you should do in any case if you're doing this kind of thing. In Lean, it's very explicit, right? I'm specifically passing a proof to this array access. There's no doubt that this will work the way I expect. There's no doubt that this will omit the runtime check. So that's great. And just to reiterate what I said earlier already, so here I'm really, so this kind of thing is really constrained to the kinds of checks that the compiler understands. Who knows whether this kind of optimization is implemented in the compiler? It is, but maybe they'll remove it, probably not, but who knows what other kinds of optimizations of this kind there could be. And as I explained earlier, with this pattern matching on empty types, for example, all kinds of optimizations are doable by the user in Lean. So these are three reasons why I think this is a bit cooler than that over there. Okay, so now I'm going to give you two examples where we use this kind of thing in this Lean standard library. which might be interesting. So we ship self-balancing binary search trees as part of our standard library. As some of you might know, there are many kinds of self-balancing binary search trees. Probably the most famous one is the red-black tree. There's also AVL trees, which were common for a while. Rust uses B trees. In the functional programming world, many languages use these weight-balanced trees. For example, Haskell has them, and so do we. And as is usual for self-balancing binary search trees, the idea is that they have some kind of property which in one way or another ensures that they have at most logarithmic size, logarithmic depth. And when I want to perform an operation on the binary search tree, I basically first do it in the naive way, where I just disregard balancing properties entirely, and then I might end up with something that is no longer balanced according to the balancing properties that I define for myself. And now I'm going to have to do rebalancing, and this usually works by moving from the bottom up in some way and then performing what's called tree rotations. So I do a constant depth pattern match on the local structure of the tree. Basically, I'm going to treat whatever is below that on these branches as a black box, and then I'm going to reorder these branches in some way that keeps the binary search tree property but restores balance. And what happens there is we are going to do some kind of nested pattern match. And for weight balanced trees, it turns out this pattern match doesn't need to be that deep, but it is still a bit of code which I have tried very hard to condense down for the slide. Here it is. No need to understand it right away. We have multiple kinds of balancing operations which need to happen for these binary search trees. So this is just one of them called left balancing, and this one happens if you have reason to believe that the left hand. So you have something that you would want to put at the root, and then you have a left and a right subtree. But whatever that is might not be. If you just put it naively, then it might not be balanced. And balance L is the right thing to do if you have reason to believe that L and R are by themselves balanced, but putting them together in the naive way would lead to something where the left subtree is at most one item too large. So this happens after inserting on the left-hand side or erasing from the right-hand side. And the precondition that is always upheld by this in the cases which we actually have is what I just said. The L and R are by themselves balanced, and L is only slightly larger than R. And it turns out if you do this, then a bunch of situations just cannot happen. So these are the balancing parameters, but it turns out in this situation down here, these two situations in this match here actually can't happen. So if you don't have any information, then you're just going to panic here, which is a bit sad because after, except for these panics, only one branch remains. So this wouldn't even need to be a branch at all here. And then this situation up here is also interesting because this situation can actually only happen in the erase case. So if you insert it in the left subtree, then this will never happen. But if you erase from the right subtree, then this might happen, which is a bit interesting. And what we actually do here is we have three versions of this function. We have the panicking one, which you just saw, and then we have this one, which is safe to call only when you only when you insert it on the left-hand side, and we encode this through these three preconditions, which are L and R are balanced, like I said, and then we have this balance L precond, which basically says the left size is only slightly too large for the thing to just be balanced. And then you can see now we have a bit of a more compact way to write down this empty pattern match that I showed you earlier. So we're going to have false.elim, which is what I can call if I'm in a contradictory context, and then I have this tick notation, which is just a custom tactic that we designed for this specifically for this use case, which basically peels away all the abstractions, does a bunch of case bashing, and then does a lot of integer linear arithmetic to prove that this situation really cannot occur in a situation where things are sufficiently balanced. And it turns out that this does make things faster. It's not a huge improvement. It's not like twice as fast to eliminate a few branches, especially because, of course, branch predictors are very good these days, and especially this one is, of course, quite late in the cascading chain of case distinctions. But 3% for a core data structure that tons and tons of people are going to use, not bad. Especially because we were, of course, comparing different implementations and different data structures for inclusion in the standard library, and red-black trees and weight-balanced trees were actually really close. But you can't do this kind of thing in this really with red-black trees. The case distinctions just aren't as complicated there, and if we hadn't been able to do these optimizations, then the weight-balanced trees would not have been faster. So it did have quite a consequence for the lean standard library. So that's nice. That's one example. Here's another one, strings. So in lean, we do strings the proper way. Strings are byte arrays, which are valid UTF-8. And we do actually track this invariant everywhere. So we have a predicate on byte arrays, which state that the predicate that a byte array is valid UTF-8, which is just there exists a sequence of characters such that our byte array is the UTF-8 encoding of the sequence of characters. So this is completely uncomputational. We don't store this sequence of characters, of course. That would defeat the whole point. But we only allow strings with byte arrays as strings which have this property. And then this means for all kinds of operations we might do on strings, we're going to propagate this invariant. So here we want to append two strings, and what we do is the byte array the underlying byte array is one byte array append the other byte array, and then we also need to prove that the result, like this appended byte array, is still valid UTF-8, and so we formulate and prove a library lemma that if you append two valid UTF-8 sequences, then you obtain a valid UTF-8 sequences. And this gives us a very rich string library in which many kinds of error cases just cannot occur anymore, which is nice. So here, for example, we are accessing. We have basically a position inside a view on a string, and we have this type of positions on a string, which is maybe a refinement type, just like you would see in liquid Haskell, which asserts that this position is either at the end or at a valid UTF-8 character boundary. So if you perform your UTF-8 decoding routine, this will not run into any errors. And you can implement this decode char function again both in C++ or in lean. We do it in C++ because it turns out implementing a theorem prover in itself, which needs to process all of its own source code, like the performance of string operations, are quite important. So doing this in C++ is worth it, but the way we wrote it, it would not be necessary. So we could remove like runtime support for strings entirely, and we would be noticeably slower, but not completely. We would not grind to a halt. Of course, the question now is this really like how much do we get from eliminating these error cases? And it turns out it depends. Like having proofs for this error case that we are not at the end of the string is useful. So this makes a noticeable difference for things like for functions that really churn through a lot of strings. For example, our identifier autocompletion. So from omitting this, we at the end check, we do benefit massively from the fact that decoding the character can never fail. That's honestly not as important, because like for UTF-8, you are checking am I 1 byte, 2 bytes, 3 bytes, or 4 bytes, and then if I'm not in any of these cases, then I'm going to fail. But of course, the vast majority of characters you're going to see in most documents are going to be 1 byte, because most characters that you see in a real document are ASCII characters. So not taking a branch that you're not even close to reaching anyway doesn't really matter that much. But I do want to spend a bit of time explaining what it takes to get there, which is actually quite a bit. So we first, so UTF-8, like we need to really understand the UTF-8 encoding, and this is because essentially a lot of operations that you might do on UTF-8 strings their correctness is really going to be dependent on the fact that UTF-8 encoding of strings is unique, and that you can encode and decode in both directions and get the same thing back that you started with. So we have a lot of these statements, which basically says if we have some kind of valid, if you're going to go ahead and decode a UTF-8 character, and we think that it has two that 2 more bytes will come after it, then the bit pattern of the thing we just looked at looks in a very specific way. So here we're using Lean's bit vector library. So this is a byte, which is part of some UTF-8 encoding, and then we're going to say, okay, we start with 1110, and then there's going to be 4 more bits, and then you get these kind of uniqueness results where you have if you have a Unicode code point that is that is 3 bytes long, then parsing this and taking the bytes and assembling them together will give the same thing if I started with the result, and then UTF-8 encode this again. And because this is an if and only if, this means these are the kinds of statements that in the end imply that encoding and decoding are really unique. So and that's a lot of work actually. And then from there you build up to more complex things, right? From there you get these things like appending UTF-8 strings, yields a UTF-8 string, or maybe you don't need the uniqueness for that, but for many other kinds of things you do. And then finally you can think about, okay, how am I now going to use this in a string library that I want to expose to people? So it's a lot of work. And we are doing like the real theory building here. We have files in the Lean standard library which don't have any code in them. They just have thousands of lines of these theorems, right? And which slowly build up this theory of UTF-8 and other things. And now I'm going to make a point about ergonomics. So the moment we said, okay, strings are going to be tracking this environment of being valid UTF-8, we actually took a bet, right? Because what happens if this doesn't scale anymore? So what if at some point I hit a proof obligation which I just can't prove because it's too difficult? And if I am in such a situation, can I somehow save myself? So for example, say I have a position in a string, I do some operation in it, and I need this to be a valid position. So I need it to be at the UTF-8 character boundary. Checking for a position, whether it is at a valid UTF-8 character boundary, is easy. I read that byte at that position, and from the bit pattern of that byte, I can tell whether it is the start of a character. So this is cheap. It is a memory access, but it's reasonably cheap. If I did something to a weight balanced tree, and maybe it's not balanced anymore, there isn't really anything I can do if I really know nothing than going over the whole tree and checking all the balancing invariants, which is linear time, which is hugely expensive. So if I decide to do this do this bundling of invariants on a large scale, then I need to trust that my theorem prover is going to support me with this to the end. I'm going to note the way this happened for binary search trees and for strings is a bit different. For binary search trees, like I said, we basically peeled away at all the abstractions and then do some kind of discharging routine, which in our case is linear integer arithmetic, but this is something you could like throw to an SMT solver and would have no problem doing it. For strings, we really did like theory building in the proper sense. a lot of handwritten proofs, a lot of well thought out like proving abstractions. And now come my strong opinions. I claim that this kind of theory building, you can do things with this where this verification generation SMT solver style will not support you. I don't think we could have done the UTF-8 if we had relied on this SMT solver for everything, even though SMT solvers are probably good at this kind of bit vector reasoning, because it is, of course, it's bit vectors, that's fine, but there are a lot of other things that we want to reason about which maybe aren't in a format that an SMT solver really supports. So I claim the system that will allow you to do this kind of thing to the end will need to be interactive. This is what I believe, because I don't want to be at the mercy of a system that I can't really control, that I can't really look into, that I can't really jump in and do the hard work if things are not looking good. On the other hand, the system will need to be automated, because otherwise things just get too difficult. Things stop scaling. I want the system to do the tedious work for me, but I do want to be able to save myself if the automation ever lets me down. And this is why I think the system needs to be interactive first and automated second, and not the other way around, because this means that I have all these abstractions, all these proper ways of doing the things myself. So that's my take, and so far from our experiences, Lean has been able to do very nice things for us in this way, and it has scaled to everything we've thrown at it, and we've shipped these things. Everything I've shown you, you can download Lean and use it today. So summing it up, so I showed you that proofs can influence compiled code if you have a system that supports it. Safety does not mean paying runtime cost, and it also does not mean, like we saw it in Rust, like hoping and needing to re-verify all the time that the compiler understands what I'm trying to tell it. Code and proofs live to live together. We should not. It would be great to not do something just because we feel the system isn't ergonomic enough. So we do need something that I can trust will scale to the size I need. Now, an interesting question is how much of the benefits can we get whilst maintaining the proofs and the code separately? Because having these proofs, having to do all these proofs immediately when I'm defining a function is sometimes annoying. It is sometimes just a bit unwieldy. And for example, we recently added a KMP implementation, so for linear time string search, to the string library, and there we generate all kinds of positions. But the reason why these positions are in bounds are actually, in many cases, non-trivial. So right now, we went for the slightly easier option of having the panics in our code, and then later, once we have developed a bunch of theory, then we prove separately that none of these panics actually happen. So we prove later that these branches will never be taken. But right now, we don't have a way to tell the compiler this after the fact and say, okay, we've shown this to you now. Please now generate more efficient code now that you've seen this proof. So that's maybe an interesting thing to think about. And that's it. Thank you very much.
Yeah, it's time for maybe one question, 1.5. You can.
Yes.
I guess this is sort of unrelated, but how did you make this presentation specifically, like mouse over
So this is a tool called, so in Lean we have a tool called Versa, which is a meta tool for building these kinds of Lean-aware documentation tools, which know about Lean very intimately. And this is an extension called Versa Slides, which is basically a Reveal.js backend for that. And it's going to be released soon. It's not released yet.
Very quick question.
Yes.
So all the code you were talking about, like the standard library, this is what you get when you just download standard Lean, and you can directly write programs in it and prove stuff.
No external library needed. Just install Lean itself, and you get all of it.
Perfect. Ben, thank you again.